Hello everyone. Today I'm presenting work by myself, Yanchao and Arash Eshghi, titled A Comprehensive Evaluation of Incremental Speech Recognition and Speaker Diarization for Conversational AI. So, jumping right in, I can say that none of these systems are yet adequate to reliably handle natural, spontaneous conversations in real time. We evaluated 3 production-level incremental ASR systems by Microsoft, IBM and Google on the switchboard corpus, which I will detail in the next slide. It is important to note here that the incremental word error rates are all roughly the same, making it impossible to distinguish between these systems using just the word error rate. So this is exactly what motivates our further analysis with additional metrics and experiments. These systems do have major differences that impact their suitability for certain use cases, in this case conversational AI, and we are reporting the incremental word error rates here. The non-incremental word error rates are reported by the companies themselves on the same corpus, and non-incremental word error rates are nearing human levels, creating a misconception that ASR is a solved problem, air quotes. We argue that this is simply not the case. Moving on to the very well-known corpus, the switchboard corpus, published in 1992, it contains dyadic human-human conversations over the phone in English on a variety of topics. These spontaneous conversations are perfect to ensure that participants are speaking naturally. So many similar datasets contain just monologues or specifically advise people to speak cleanly. And by cleanly, I'm referring to the fact that natural conversations are very messy and littered with disfluencies. So people talk over one another, restart their sentences, correct themselves mid-sentence, fill pauses with ahs and ums, etc. So we process all of these phenomena through our everyday conversation, making them a very important aspect of this corpus. The audio in switchboard is separated by speaker, as it was over the phone, which allows us to run overlap-related experiments, and similarly, in-depth disfluency annotations were added to switchboard in 1995, allowing us to run disfluency-related experiments. You can see an example of a self-correction in that last sentence. Now, before I dive into our results, I will quickly run through an example to illustrate the difference between an incremental and non-incremental speech recognition system. Here we have the outputs of 4 systems when a user says, "Take the red cross." Starting on the right-hand side with output D, the yellow diamond indicates when the transcription was output. So, this system is non-incremental. The user says, "Take the red cross," and the system, after a short pause, outputs "take the red cross," after the user has finished the full utterance, so not word by word. Example C is very similar, however the system is more timely, outputting the whole utterance transcription before the user has even finished saying the word cross. In example B, we have an incremental system. The system outputs the word take before the user has even finished the word, then outputs the as the user finishes saying the, but then the system outputs right after the user has said r. So the system continues to listen and substitutes that hypothesis with red as the user finishes uttering that word. The system hears what it thinks the word is right, outputs that, and then retracts that hypothesis and replaces it with red when it realizes that the correct word is red. Finally, the system correctly outputs cross once it thinks it has figured out that particular word. So system A is the perfect system, more stable than system B, as it waits and doesn't have to substitute its hypothesis, but it's still timely and accurate. So in conversational AI, the output of our incremental ASR systems feed downstream components, such as our incremental NLU, which can start processing what the user is saying as they say it, like we all do. So if a system regularly substitutes its hypotheses, these downstream components all have to reprocess too, which is of course not desirable. Now on to our more in-depth findings. This metric, the first occurrence or FO latency, not F0, reports the time between the first system hypothesis of a word and the time that the word started to be uttered. So it's the time that the incorrect hypothesis right was output in the example before, minus the time that the word red began to be uttered. So in this chart we can see in blue that Microsoft almost always outputs its first hypothesis within a fraction of a second. And Google in green is similar, although usually takes a little longer than Microsoft. In orange, IBM takes quite a lot longer to output its first hypothesis, often taking around 1.5 seconds from the beginning of the word to hypothesize what that word is. An important note to add is that these timings are output from the systems themselves. They do not include any network latencies. And this difference is intriguing and even more pronounced when we look at the FD latency. The FD latency is the difference between the final hypothesis being output by the system, so the hypothesis of a word that never gets retracted, and the time that the word finishes being uttered. So again, if the system updates its word prediction from right to red, it's the time that red was output minus the time that red was finished being uttered. This latency is negative when the final hypothesis is output before the user has finished saying that word. Microsoft and Google, in blue and green respectively, almost always make their final decision before or as the person finishes saying that word. IBM, however, in orange, often changes its mind 4 seconds after the user has finished that word. This major difference and the longer FO latencies are due to IBM's less frequent hypotheses. Both Microsoft and Google output hypotheses extremely frequently, whereas IBM outputs word hypotheses in, I would call them, batches. I do not think it's unfair to include IBM in this evaluation, as they do state that their system is for interactive applications and real-time transcription, but I will note, however, that there are other use cases for incremental ASR systems, so I'm not saying that IBM performs poorly here, just that it is less suitable for conversational AI uses. As explained, these delays would require all downstream components to reprocess words 4 seconds after they were uttered. One benefit of longer hypothesis times is initial stability. If we look at the word survival rate, we can really analyze each system's stability. So the lines represent the percentage of word hypotheses that are final at a given age of that word hypothesis. So the lines cut the y-axis at the percentage of hypotheses that never change. So IBM, the orange line, may take longer to output its hypotheses, but over 90% of them remain unchanged. The large step in the orange line is again a factor of IBM's batched outputs. So the initial stability is great, but when an update is required, it is quite delayed. So I will highlight that this stability is not the number of hypothesis changes, but the time that it takes for our system to stabilize. So Microsoft, for example, the blue line, outputs an extremely large amount of word predictions, hence the very smooth line, but downstream components can trust that even after just 0.4 seconds, say, after its initial hypothesis, 95% of them will remain unchanged. Google, the green line, outputs hypotheses less frequently than Microsoft, and IBM's initial stability is never taken over by Google. Moving on to our experiments, we started using the split audio channels. In all of our results above, we combined the audio of both speakers to mimic the standard setting of a conversational agent. That is, it sits in a room hearing both speakers in its microphones. These conversations were over the phone, however, in switchboard, so the audio was picked up by separate microphones and can be split. We did this to ensure that overlap did not impact our disfluency results. We ran this split audio through the same incremental ASR systems and compared to the reference for an original word error rate in this experiment. We then cleaned the reference. To highlight, we used the same system output transcriptions but changed the reference. We carried out various experiments around self-corrections, edit terms, and filled pauses, and then we could clean these from the reference using the disfluency annotations by Mathieu et al. In 1995. We found that no system seemed to handle self-corrections or edit terms in a special manner. However, when we filtered filled pauses from the reference, we found something interesting. Now, for clarity, filled pauses are ums and ahs, etc., that we all litter throughout our conversations. They often indicate hesitation and confusion, making them quite valuable for a conversational agent. So, Microsoft had an increased error when we removed filled pauses from the reference, and this is expected as the reference no longer matches the actual spoken audio. IBM, however, had almost no change in word error rate, and Google even managed to improve, suggesting that both of these systems filter filled pauses in real time, Google slightly more accurately than IBM. Now, this removes valuable information for downstream components. But in the use case of live captioning, so captioning an ongoing Zoom call, for example, this is actually a plus point, hence the design decision to do this. In our final ASR experiment, we investigated each system's robustness to overlaps. We compared the word error rates of the audio and reference transcriptions of both speakers together, and we then did the same using the split audio and separate reference transcriptions. We are reporting the least worst improvement in word error rate for each system across all the conversations. So Microsoft and Google perform roughly the same here, but IBM is the most robust to speech overlaps. So given all of the switchboard conversations, IBM transcribed a maximum of 14.76% of a conversation incorrectly due to overlaps. And overlaps are extremely common in dyadic conversations, but conversational agents are increasingly expected to engage in multi-party settings with an unknown number of people. We therefore investigated the real-time speaker diarization components of the same systems to see how they perform. For clarity, speaker diarization partitions an audio stream into speaker-labeled segments, and these can be combined with ASR systems and must also work incrementally if we are able to produce naturally interactive conversational agents. Only IBM and Google have real-time speaker diarization systems available, hence why Microsoft is missing from this table. The diarization error rate, or DER, is the standard speaker diarization metric and takes many factors into consideration, including the percentage of time that a speaker is incorrectly labeled as another speaker, the percentage of time that a non-speech region is identified as containing speech, and the percentage of speech regions that are identified by the system as containing no speaker. On the switchboard corpus, IBM outperforms Google by a huge margin, and Google's high error rate is mainly due to labeling speakers incorrectly. All of Switchboard's conversations are dyadic, so we decided to evaluate the same systems again on another corpus called AVDR. This corpus contains conversations of up to 4 people, and it does contain video, but we only use the audio here. Both systems report considerably worse results on AVDR. IBM outperforms Google again, but it is wrong almost 50% of the time. And all speakers are picked up by a single microphone in AVDR, so unfortunately, the context of a conversational agent. We can therefore conclude that none of these systems are yet adequate to reliably handle natural, spontaneous conversations in real time. Microsoft does have the most suitable incremental ASR system for conversational AI, IBM has the leading real-time speaker diarization system, and Google is a balance between the two. We hope that by releasing our evaluation framework, we will encourage future assessment of such systems and promote the design of speech recognition and diarization systems with the above metrics in mind. Thank you.